Hello everyone. Today's discussion will be based on the new problems on the phenols. As we have gone through the modes of preparation of phenols, physical as well as chemical properties. Now based on that, we are going to list some problems on the phenols. So without wasting our time, we will start with this problem. So we are given a particular compound. This compound reacts with oxygen from air, which gives you compound A, and this compound A on acidification with mineral acid gives you compound B. Now we have to identify this compound A and B. Now look at this compound. This compound is one of the very important reaction for the preparation of phenols, and that method of preparation is known as preparation from cumene. So this compound is that compound which is known as cumene. So cumene on reaction with oxygen gives you A on acidification gives you B. So we started with this compound cumene C6H5CH3 all twice. This is our starting compound cumene. Cumene reacts with oxygen from air, that is aerial oxidation of cumene. Now we know this oxygen is a very good oxidizing agent. This is also a diradical. So this reacts with cumene to give you cumene hydroperoxide. So the first compound formed is cumene hydroperoxide, that is compound A. Now this cumene hydroperoxide on acidification, this undergoes rearrangement of this phenyl group from carbon to oxygen. During the course of rearrangement, a particular species is formed in which the positive charge appears on oxygen. So that is an electrophilic oxygen is formed, and to this electrophilic oxygen a phenyl group migrates from carbon to electrophilic oxygen. Finally, that rearranged species on reaction with water gives you a very important compound, that is phenol, that is our product, plus an industrially important compound, that is acetone, is also formed. So in this particular reaction, a very important byproduct, that is the acetone, which is one of the most important organic solvent. So along with this acetone, we are getting phenol. So this is an industrial method for preparation of phenol. So cumene hydroperoxide, this is our A, and the final product, this is our B, that is phenol. This is cumene hydroperoxide because we have a peroxide bond here. In the second problem, we are starting with salicylic acid, orthosalicylic acid. So this orthosalicylic acid reacts with A, followed by heating gives you phenol. That means from the starting salicylic acid we are removing carbon dioxide. So this is decarboxylation. The reaction is decarboxylation. So we have to choose a particular reagent so that this carbon dioxide is effectively removed from salicylic acid. So this the reagent of choice for removal of carbon dioxide, that particular A, this is our soda lime. So acids on heating with soda lime is a mixture of sodium hydroxide and calcium oxide. Now carboxylic acids on heating with soda lime, that is a mixture of sodium hydroxide and calcium oxide, undergoes decarboxylation, that is a molecule of carbon dioxide is removed and this is converted into the hydrocarbon. So we started with this phenolic compound containing COH at ortho position, heating with this soda lime. This soda lime is an effective decarboxylating agent which removes carbon dioxide and is converted into phenol. So the reagent that we have to use here is soda lime. In the next problem, we have a sequence of reagent and the reagents also given to you. Starting compound is given. We have to find the intermediate compound form, that is A, B and C. Now look at this. We are starting compound is toluene. Toluene reacts with alkaline KMnO4 followed by acidification gives you compound A. Now we know KMnO5 is a very strong oxidizing agent, and the starting compound is phenol containing benzene containing side chain, that is methyl. So whenever we have this substituted alkyl substituted benzenes on reaction with KMnO4, the side chain group, that is alkyl group, this side chain alkyl group is always oxidized by KMnO4 to carboxylic acid. So this toluene on reaction with KMnO4 in alkaline medium will get salt of carboxylic acid, which on acidification gives you acid. So we get this carboxylic acid, that is the benzoic acid. So toluene on oxidation with alkaline KMnO4 gives you benzoic salt of benzoic acid, which on acidification gives you benzoic acid. That means KMnO4 will oxidize the side chain present in the benzene ring to carboxylic acid group. So this is one of the very good method, or one of the method for preparation of aromatic acids from substituted benzenes. Now we have this A, this is our A. Now A on reaction with sulfuric acid. Now this COOH acidic group, this is meta-directing group. So once we have this meta-directing group, benzene ring containing meta-directing group on electrophilic substitution reaction, substitution goes to the meta position. So this is sulfuric acid concentrated followed by heating. That means we are treating this substance with sulfuric acid. So the reaction is sulfonation. This is our A. A reacts with sulfuric acid concentrated followed by heating. So this is sulfonation. So since acidic group being a meta-directing group, the electrophile will goes to the meta position. So we'll have substitution at meta, there is sulfonation at meta position. So we have sulfonation at meta position. So this is our compound B. So benzoic acid sulfonation by use of concentrated sulfonic acid gives you substitution at meta position, because acid group is meta-directing group. Now this compound B on heating with sodium hydroxide means fusion with sodium hydroxide. So first we have look at this acidic group. This acidic group on the reaction with sodium hydroxide, this is converted into sodium salt. So simply this is acid base reaction. Now this sodium salt which is further heated with sodium hydroxide. So reaction says this is heating with sodium hydroxide. So fusion with sodium hydroxide. Then desulfonation takes place and phenolic group is formed. So this gives you sodium salt of benzoic acid and phenoxide ion is formed. So this phenoxide ion on acidification gives you this is our compound E, this is our compound B, and this is our compound C. So this is one of the methods of preparation of phenol from sulfonic acid. Benzene sulfonic acid on heating with sodium hydroxide, fusion with sodium hydroxide, desulfonation takes place, and in place of this sulfonic group, an OH group is introduced. OH group of phenol being acidic further reacts with this to give you phenoxide ion, which on acidification gives you phenol. So this is how we prepare phenols from benzene sulfonic acid. So instead of benzene sulfonic acid, we are starting from this toluene. So by starting from this toluene, we are introducing sulfonic acid group by sulfonation. Now look at this next problem. Again we have a sequence of reaction. In this sequence of reaction, the starting compound is benzene, reacts with oleum taken in excess amount, followed by heating, which gives you A on the reaction with aqueous sodium hydroxide gives you B on heating with sodium hydroxide fusion with sodium hydroxide gives you C on acidification gives you compound D. Now this reaction is almost similar to the previous reaction, which is already shown here. So the first reaction is benzene, starting with benzene. So we have starting compound benzene. Benzene reacts with oleum. So oleum is a very strong sulfonating agent, followed by heating. Question says this is taken in excess amount. So this undergoes sulfonation. So reaction is sulfonation of benzene. So benzene on sulfonation gives you benzene sulfonic acid. Now this oleum being taken in excess, so this undergoes further sulfonation. So in the second step, this sulfonic group, look at this group, this is meta-directing group. So this undergoes further sulfonation, and second sulfonic group is introduced at meta position. So the compound A forms this meta substituent. This is compound A. So benzene on heating with sulfonic acid or oleum taken in excess, sulfonation takes place, and sulfonic groups are introduced at meta to each other. Now this sulfonic acid group on reaction with sodium hydroxide aqueous, so we have acid reacts with base to give you salt. So sodium salt of sulfonic acid is formed. Now this is our compound B, that is simply acid base. This is acid, this is base, so acid base reacts to give you salt. So this compound B, sodium salt of sulfonic acid on fusion with sodium hydroxide, that is heating with sodium hydroxide, as I have shown you reaction here. Sulfonic acid or sodium salt of sulfonic acid on fusion with sodium hydroxide, desulfonation takes place and a OH group is introduced to the benzene ring. So as it is, so we have this ONA and ONA, sodium salt of phenol is formed. This sodium salt of phenol on acidification gives you phenol, that is both OH groups at 1,3 position. So this is simply nothing but the preparation of phenol from benzene sulfonic acid again. And next reaction, again the starting compound is toluene. We are starting with toluene. Toluene is made to react with this reagent. So we have this oxygen in presence of MnCl2, manganese chloride, and cupric chloride, followed by heating, or we can take this combination, means oxygen in presence of manganese ion and cupric ion, followed by heating. Now this particular reaction is a method for conversion of toluene into phenol. So if suppose we want to convert this toluene, there is oxidation of toluene to phenol. So direct oxidation of toluene to phenol can be carried out by oxidation with oxygen, followed by heating with a mixture of manganese chloride and cupric chloride, or manganese sulfate or cupric sulfate. So this converts this toluene into phenol. So direct conversion of toluene into phenol is by oxidation with oxygen in presence of manganese salt and cupric salt, followed by heating. So the product formed here is phenol. Again, next reaction we have a sequence of reaction. The starting compound for this sequence of reaction is nitrobenzene. So nitrobenzene first reacts with oleum, which gives you A. A on heating with sodium hydroxide gives you compound B. B on acidification gives you compound C. So we have to identify A, B and C. So now look at this. We are using sulfuric acid, concentrated sulfuric acid or oleum. So this is a very strong reagent for sulfonation. So the first step is sulfonation. That means sulfonic acid would be introduced to nitrobenzene. So now look at this. This nitro group is meta-directing group. So this being a meta-directing group, sulfonation will take place at meta position. So the first compound A is sulfonation at meta position. So we have this NO2SO3H. So nitrobenzene, nitro group being meta-directing group, that is electron withdrawing, we require a much stronger sulfonating agent, that is oleum. So oleum reacts with nitrobenzene and sulfonation takes place at meta position. So this is A. Now A, sulfonic acid on fusion with sodium hydroxide, we have seen earlier reaction. Sulfonic acid group fusion with sodium hydroxide gives you sodium salt of phenol. So this means sulfonic group will be undergoing desulfonation and phenolic group will be introduced. So this is compound B. So compound B is sodium salt of phenol. So sodium salt of phenol on acidification gives you phenol. So these are nothing but the methods of preparation of phenol from sulfonic acid. So we have this 3-nitrophenol is the final product by this sequence of reaction. In the next sequence of reaction, we have given the starting compound, that is benzene. Benzene undergoes a sequence of reaction to give you compound A, B, C and D. We have to identify the compounds A, B, C, D and in this particular reaction. So now for this we have to identify the reagent, what is this reagent used and which reaction is to be taking place by use of this sort of a reagent. Now look at this. In the first reaction we are using a mixture of concentrated nitric acid and concentrated sulfuric acid. This mixture is what we call as nitrating mixture. So starting with benzene. Benzene reacts with nitrating mixture. So the first reaction is nitration. So benzene reacts with nitrating mixture and this gives you nitrobenzene. So the first reaction is nitration. So nitration of benzene by use of this nitrating mixture, which is nothing but concentrated sulfuric acid and concentrated nitric acid. So we have nitrobenzene. Now this nitrobenzene is made to react with zinc HCl. Now look at this. We are using metal. We have this nitrobenzene. To this we are using zinc HCl. So zinc HCl is nothing but a reducing agent. So nitrobenzene reacts with zinc HCl. So this nitro group will be reduced to aniline. So this reduction of nitro group. So we cannot use a much stronger reducing agent. If you are using a much stronger reducing agent, then benzene will be reduced to cyclohexane. So we are using a milder reducing agent which only reduces the nitric group into aniline. So this is our compound B, that is aniline. Now aniline reacts with sodium nitrite and HCl. So a mixture of sodium nitrite and HCl. This mixture produces nitrous acid. So aniline reaction with nitrous acid, this NH2 group is converted into diazonium ion, benzene diazonium ion. So the compound C is benzene diazonium ion. So benzene diazonium ion which on reaction with steam, that is H2O followed by heating. So benzene diazonium ions on steam distillation nitrogen gas is evolved and a phenolic group is introduced, plus nitrogen gas will be released. So this is again one of the methods of preparation of phenol from benzene diazoniamine. So instead of benzene diazoniamine, we are starting from benzene. First nitro group is introduced by nitration, then nitro is reduced to aniline, aniline is converted into diazonium ion, and further this diazonium on steam distillation gives you final product, that is phenol. So this compound is on product D, that is phenol. So in this sequence of reaction, the final product is phenol. So we are converting benzene into phenol via this reaction. In the next problem, we are starting with phenol. Phenol by this sequence of reaction is converted into product D. Now we have to identify what is the product D. Between this we have A, B, C. So we have to identify what is the structure of A, B, C and D formed in this particular sequence of reaction. Starting compound is phenol. Phenol reacts with dilute nitric acid. So we are using nitric acid. Phenol OH group is a very strong activating group, which is nothing but ortho-para directing group. That means this phenol containing a very strong ortho-para directing group, OH group, reacts with dilute nitric acid. So nitric acid is nothing but a nitrogen reagent. So the first reaction is nitration. So nitration of phenol can be carried out by use of dilute nitric acid. The reason being, phenolic group is a much stronger activating group, and this is ortho-para directing group. So the nitro group will be introduced at ortho and para position. So we have this nitric acid. So the first compound form. So we have, look at this, phenol. Phenol reacts with dilute nitric acid. When nitration takes place, this gives you a mixture of ortho and para. Plus para compound will be formed. So a mixture of ortho and para nitrophenol is formed. This is our A. Now A reacts with zinc HCl. Now we have shown the reaction earlier. Nitro group on reduction with zinc HCl, nitro group is reduced to NH2. So we have this reducing agent where nitro is reduced to NH2. So we have OH, NH2 and this para isomer OH, NH2. So this is our B. Now this B reacts with sodium nitrite HCl. So sodium nitrite HCl gives you nitrous acid. This nitrous acid converts aniline NH2 into diazoniamine. So this reacts with nitrous acid, that is nothing but a mixture of sodium nitrite and HCl. When this gives you OH N2 plus so we have benzene diazoniamine. So this is our compound C. Now this compound C on acid heating with steam, water के साथ heat किया at very high temperature means steam distillation. When phenolic group is introduced to benzene ring, that means nitrogen gas is removed and phenolic group is introduced here. So this is our product D. So phenolic group being a very strong activating group, nitration can be carried out by use of a weak nitrating agent, that is dilute nitric acid. In this reaction, starting compound is phenol. So phenol reacts with sodium hydroxide, which gives you A. A reacts with a number of reagents to give you these products. We have to identify A, B, C, D, E. So for this, now look at this, we have to consider on the first reaction. This phenolic hydrogen is acidic. Now since we have acidic hydrogen, so this acid reacts with base. So the first reaction is acidic phenol reacts with sodium hydroxide base to give you A. So A must be your salt, that is sodium phenoxide. So acid reacts with base to give you salt. So A is your sodium phenoxide. So we have O minus Na plus. So this is our A, sodium phenoxide. Now sodium phenoxide reacts with Rx, that is alkyl halide. Now this sodium phenoxide O minus is a very good nucleophile. So this undergoes SN2 reaction. So O minus attacks alkyl group and this X minus is removed. So this gives you OR, that is phenolic ether is to be formed. So this is one of the methods for preparation of alkyl aryl ether. So phenol is converted into phenoxide. Phenoxide reacts with alkyl halide to give you SN2 reaction, via SN2 reaction to give you alkyl aryl ether, that is Williamson ether synthesis. This phenoxide also reacts with RC double bond OCl, acyl halide. Now look at this. Carbon of acyl halide is attached to two strong electron withdrawing group, that is oxygen as well as chlorine. So this carbon of acid halide is electrophilic. This electrophilic carbon reacts with nucleophilic oxygen. So this nucleophilic oxygen attack this electrophilic carbon and form this Cl minus is released, and this gives you acylation. So we have O C double bond O R, that is ester will be formed. So phenol can be converted to phenolic ester via reaction with this acid halide, that is nucleophilic acyl substitution. If in this particular reaction, if R happens to be aryl, that is RCOCl, so instead of this alkyl we are using benzene ring COCl, acetyl. Phenol, sodium salt of phenol reacts with benzoyl chloride. This is benzoyl chloride. Instead of R we have placed aryl group. The reaction is exactly same. The only difference is instead of R we will have aryl group. So the reaction of phenol with benzoyl chloride give you this product. This reaction is known as Shorten-Bowman reaction. So Shorten-Bowman reaction is reaction of phenols with benzoyl chloride. This A, sodium salt of phenol, also reacts with diazomethane CH2N2. Now this diazomethane, the reaction of phenoxide with diazomethane is a very good method for preparation of ether. So this generates methyl diazonium. Methyl diazonium generates methyl carbene. Methyl carbene undergoes insertion reaction with this phenol to give you ether. So this was our compound E. This is compound B. This is compound C. This phenoxide also reacts with dimethyl sulfate. This is dimethyl sulfate. Now we have seen this O minus of phenol is a very good nucleophile. So this nucleophile attacking this carbon, that is again SN2 reaction. So ये यहाँ पे अटैक किए और यहाँ से O minus release किया. When this gives you again ether. So these are the various reactions that can be carried out with this phenoxide ion. So in this phenol reaction, phenoxide is acting as a very good nucleophile this nucleophile phenoxide reacts with electrophilic reagents. In case of alkyl halide, reaction via SN2 to give you alkyl aryl ether. On the other side, this reacts with acid halides. Again, the carbon of acid halide is electrophilic. So, nucleophilic oxygen attacks electrophilic oxygen, and from this X minus or Cl minus is released to give you phenolic esters. If instead of this alkyl group, if benzene ring is used, that is benzylation. So, benzylation of phenol with benzoyl chloride is known as Schotten-Baumann reaction. Next, we have phenoxide reacts with diazomethane. Diazomethane generates carbene. Carbene reacts with phenol to give you insertion reaction, that is ether again, alkyl aryl ether. Again, this phenoxide ion reacts with dimethyl sulfate. Again, this gives you alkyl aryl ether. So, this is good method for preparation of alkyl aryl ether, especially methyl group is to be introduced. Next reaction, next problem. We are starting with phenol. Phenol reacts with benzene, diazonium ion to give you some product. So this is a reaction of phenol with benzene, diazonium in presence of alkaline medium. So this reaction is what we call as coupling reaction. So this particular reaction of phenols with benzene, diazonium ion, this reaction is used for testing of phenols. If suppose we have to confirm the presence of phenolic group, then we can use this reaction. So this is test for phenol. So phenols on reaction with benzene, diazonium ion gives you azodies. So reaction is, we have this phenol reacts with benzene, diazonium ion N2. So benzene, diazonium, and look at this, nitrogen with positive charge is an electrophile. So we have an electrophile. Benzene ring containing OH. OH of phenol contains two lone pairs of electron, which is in conjugation with benzene ring. So this OH group is a very strong electron releasing group. So we have a nucleophile. So this electron, due to resonance, electron density is increased at ortho and para position. So due to symmetrical region, the para position attacks this electrophilic nitrogen. When this gives you this compound, so we have this. So this compound is a colored substance which is known as azodies. Color substance. So phenols on the reaction with benzene, diazonium ion in presence of alkali, mild alkali, coupling reaction takes place between phenol and azonium ion. This is nothing but electrophile-nucleophile reaction. And coupling may take place ortho and para position, but because of symmetry, ortho or para position is forming as a major compound, and in case of ortho, steric hindrance will be there. So we are just showing the major compound. So major product is azodies, which are colored substance. So this can be used as a test for phenols. Next reaction is the reaction of phenol with phthalic acid. This is phthalic acid. Phthalic acid reacts with phenol in presence of concentrated sulfuric acid. This gives you a product. So this is again a very important reaction of phenol, which is again used as a test for phenol. So this can also be used as a test for phenol. So phenol reacts with phthalic acid in presence of concentrated sulfuric acid. So what is happening is, this phthalic acid on reaction with concentrated sulfuric acid is heating with concentrated sulfuric acid. A molecule of water is removed and this is converted into phthalic anhydride. So this is phthalic anhydride. Now It is this phthalic anhydride that will react with phenol. So first reaction is, instead of this phthalic acid, we can also directly write down the phenol plus phthalic anhydride in presence of sulfuric acid, what is the product. Or if reaction says phenol plus phthalic acid in presence of sulfuric acid, so the first reaction is phthalic acid reacts with sulfuric acid, undergoes dehydration to give you phthalic anhydride, and this phthalic anhydride reacts with phenol to give you the very important compound which is known as phenolphthalein. That is one of the very good indicators that we use in acid-base titration. So this phthalic anhydride reacts with 2 moles of phenol, again in presence of sulfuric acid, and this gives you a compound that is known as phenolphthalein. This is phenolphthalein. This compound is known as phenolphthalein. So this is known as phthalene test. So phenol react with phthalic acid in presence of sulfuric acid. First phthalic acid is converted to phthalic anhydride. Phthalic anhydride further reacts with 2 moles of phenol to give you phenolphthalein, which is a pink color compound that is used as an indicator for acid-base titration. So this is also test for phenol, phthalene test, formation of phenolphthalein from phenol and phthalic acid. Next reaction is reaction of phenol with chloroform in presence of alkali. So reaction of phenol with chloroform in presence of alkali. So now look at this. We have this chloroform. Chloroform reacts with base when this gives you CCl3 minus plus H2O. So this hydrogen of chloroform being acidic is withdrawn by base to give you CCl3. Now this CCl3 undergoes decomposition to give you dichlorocarbene plus Cl minus. So this is the reagent or the electrophile which is used for this reaction. That is dichlorocarbene. So dichlorocarbene. So in this reaction, the electrophile is dichlorocarbene. So dichlorocarbene reacts with phenol. Now look at this. Phenolic group is strong electron withdrawing, electron releasing group, as I have shown you earlier. Now we have strong electron releasing group. So this phenolic group is nucleophile. Now chloroform base, this gives you dichlorocarbene. So we have an electrophile. So this reaction is electrophilic substitution reaction. So this OH group being ortho-para directing group, electrophilic substitution takes place at ortho and para, and this CCl2 further hydrolyzed by sodium hydroxide when this gives you OH reacts with CCl2 in presence of OH minus when this gives you O minus CHO. A formyl group is introduced at ortho position and the para position. That is formylation at ortho and para. Now this on acidification gives you phenolic compound. So we have CHON plus para isomer. So this compound, so this reaction is what we call as a very important name reaction of phenol, which is known as Remer-Tiemann reaction. So reaction is Remer-Tiemann reaction. So Remer-Tiemann, by this Remer-Tiemann reaction, we can introduce a formyl group CH group, aldehyde group to the benzene ring. So this is a specific reaction of phenols. Phenols react with dichlorocarbene, that is chloroform, in presence of alkali. When dichlorocarbene electrophile is generated and formyl group is introduced at ortho and para position. So this is the ortho or para group substituted product is known as salicyl dehyde. So the product is salicyl dehyde. salicyldehyde. So if you look at a salicyldehyde, now the starting compound is phenol, the final product is CH group is introduced. So the introduction of CH group. Now what is the change in molar mass? So we have replaced this hydrogen of benzene by C double bond O. So the mass of C double bond is 28. So during this product formation, reaction of phenol with chloroform in presence of sodium hydroxide, there is increase in mass by 28 mass unit. There is change in mass by 28 unified mass. Because look at this, एक hydrogen था, as it is a, instead of this we are introducing C double bond O. So mass of CO is carbon is 12, oxygen is 16, this is 28. So there is increase in mass by 28 units in Riemann-Tiemann reaction of phenol with chloroform in presence of alkali. Or there is a change in mass by 28 mass unit. Okay, this reaction is also exactly identical to the problem number 12. So we started with phenol plus chloroform in presence of sodium hydroxide or potassium hydroxide in presence of alkali. The only difference is in problem number 12, no substitution is present in ortho and para position, whereas in problem number 13, a methyl group is placed in ortho position. So when ortho position is blocked, then the substitution reaction will take place at para position. This is simple because already this we have methyl group at ortho position. So this ortho we cannot undergo substitution at this ortho position. So ortho position being blocked, the major compound will be common, that is para. So this is again a Riemann-Tiemann reaction. So the final product will be OH and CH group, that is para-salicyldehyde will be formed as a major compound if the ortho position is blocked by any group. अब ये कहेंगे why not substitution at this ortho? Because if we have substitution this at this particular, this will have enormous amount of steric hindrance. To avoid this steric hindrance, the major product will be substitution at the para product. Now in problem number 14, the problem number 14 is slight modification of number 13. So we have introduced methyl at para position instead of ortho position. Chloroform with alkali gives you product A and B. We have to identify. So now if para position is blocked, then we can have substitution at ortho. So 1A will be substitution at ortho position. So we have CHO. Now we have to identify this product B. What is this abnormal product B? Now to define this abnormal product B, we have to go through the mechanism again. Slightly I'll show you the mechanism. This gives you dichlorocarbon. Dichlorocarbon will have to react with this. Now we have this phenol. Phenol is acidic, react with base to give you phenoxide. So we have O minus. So now this electron is conjugation with benzene ring. So this reacts here, and this para carbon aqueous negative. So because of this resonance, we have this double bond, double bond, double bond O CH3 with negative. So this negatively charged para carbon reacts with CCl2, that is dichlorocarbon. So this being electrophile, ये attacks one. When this gives you CH3 Cl2 minus. Now look at this. This OH minus reacts with H plus and to give you water, and finally this reacts with water. Why? Because carbon minus is a much stronger base than OH minus. So this water will act as an acid. This will act as a base. So finally this gives you CH3 CHCl2. This is the abnormal product that is being formed. The formation of this abnormal product again proves that this reaction might have gone through the formation of this dichlorocarbon. So in fact, isolation of this compound proves the electrophile in this reaction is dichlorocarbon. This compound does not undergo hydrolysis because of the steric hindrance. This Cl minus, look at this, we have CH3, we have a benzene, so the real side attack is not possible, so this cannot undergo hydrolysis to give you CHO group. So this is the abnormal product that is being formed here in this reaction. So this abnormal product is formed when we have a para position being blocked by any particular group. So since this does not have any hydrogen, so this cannot rearrange to give you phenoxide, so this is dienone is formed. Now in problem number 15, again we have this phenol. Phenol is to be reacted with carbon tetrachloride. Now as we have seen earlier, phenol OH group is a very strong electron releasing group which releases electron density to ortho and para position by resonance. So we have this ortho para directing group CCl4. Carbon tetrachloride, carbon is bonded to 4 strong electron withdrawing group. Because of electron withdrawal by 4Cl, this carbon is electrophile. So this is electrophile. So this being electrophile, OH group of benzene being electron releasing, this is nucleophile. So this undergoes nucleophile electrophile reaction. So this is nothing but electrophilic substitution reaction. Now because of this being ortho para directing, electron density at ortho and para is increased. So substitution reaction will take place at ortho and para position, and this Cl will be replaced by OH, that is hydrolysis. When this gives you OH and COOH, means first discussion followed by acidification. So ACOOH group is introduced at ortho and para position. This compound is known as salicylic acid. So now when we use chloroform, an aldehyde group was introduced at ortho and para position if we have a pure phenol. Instead of chloroform, if you are using carbon tetrachloride, then an acid functional group is introduced at ortho and para position. So this reaction is also known as Reimer-Tiemann reaction. So in Reimer-Tiemann reaction, either we can use chloroform or we can use carbon tetrachloride, but the product will be different. If chloroform is used, then an aldehyde group will be introduced, that is known as formylation. But if we use carbon tetrachloride in presence of alkali, then acidic functional group will be introduced at ortho and para positions under both this Reimer-Tiemann reaction. In problem number 16, there is a reaction between phenol and carbon dioxide in presence of sodium hydroxide, which gives you compound A. A on reaction with acetyl chloride gives you compound B. We have to identify A and B. Now look at this. We have a carbon dioxide, sodium hydroxide, phenol. So now look at this. This phenolic group, as we have seen, this is a much stronger electron releasing group which increases electron density at ortho and para position by resonance. Now we have carbon dioxide. So carbon is bonded to 2 strong electron withdrawing groups. So this carbon of carbon dioxide is electrophile. So we have a nucleophile, we have an electrophile. So this is nothing but electrophilic substitution reaction. Now the question is, what is the purpose of this sodium hydroxide? The purpose of sodium hydroxide is to remove this acidic hydrogen so that this is converted into much stronger electron activating group, that is phenoxide. So we have looked at this. Phenol reacts with OH minus, so we have acid base reacts to give you sodium phenoxide. So this sodium phenoxide being resonance stabilized increases electron density at ortho and para position. So this is the reason why this is to be converted into phenoxide, and so that this becomes a much stronger electron releasing group, means much stronger activating group. This further undergoes delocalization. So now look at this. If suppose this, let's have this 1, this is 2. If look at this intermediate one reacts with carbon dioxide. So now look at this nucleophile attacking electrophilic carbon, and this electron is shifted to oxygen. When this gives you HC double bond O, O minus double bond O, double bond, double bond. Now look at it, this undergoes elimination of H plus ion. When this gives you phenoxide. Now because this is formed because we are having a strong basic medium. So in basic medium, both phenolic hydrogen and acidic hydrogen will be removed, which on acidification gives you salicylic acid. So phenol reacts with carbon dioxide in presence of sodium hydroxide, gives you an acidic group is introduced at phenol ortho and para position. So this is similar to this Riemann-Tiemann reaction. So in case of Riemann-Tiemann reaction, we are using carbon tetrachloride, but in case of this reaction, we are using carbon dioxide in presence of sodium hydroxide. So this is our A plus. If we start with this 2, this will give you para product. So 2 reacts with carbon dioxide, this gives you para substitution. So both we have to get it. This is compound A, that is salicylic acid. So this conversion of phenol into salicylic acid by use of this carbon dioxide, so this reaction is known as Kolbe-Schmitt reaction. So Kolbe-Schmitt reaction is a reaction of phenol with carbon dioxide in presence of sodium hydroxide when an acidic group is introduced at ortho and para position. So if you look at this Kolbe-Schmitt and Riemann-Tiemann reaction, starting compound is same, final product is same, medium is same, the only difference is the choice of reagent. In case of Riemann-Tiemann, we are using carbon tetrachloride, whereas in case of Kolbe-Schmitt reaction, we are using carbon dioxide as a reagent. So in both the case, starting compound is phenol, final product is acid, medium is basic medium, there is change in the different reagent. Now this reacts with, in this reaction, ortho will be forming as a major compound. This is ortho, this is para, so ortho is major here. Now this ortho, why this ortho is forming major compound? Because this can stabilize through intramolecular hydrogen bond. So because of this, this is forming as a major compound. Now this A, that is the major compound, OH reacts with CO2H with acetyl chloride. Now what is happening is, this group, this is our electrophile because this is attached to 2 strong electron withdrawing group. So this being electrophile, there must be a nucleophilic site to attack this. So already we have seen reaction of phenol with acid halide, that is acylation reaction. So now look at this, oxygen of phenol attacks this electrophilic carbon when this gives you acylation at oxygen. So this is acetyl salicylic acid, acetyl salicylic acid, which is a very important drug which is known as aspirin. ये एनाल्जेसिक है, पेन किलर है, सर दर्द वगैरह में हम लोग यूज करते हैं, दैट इज नथिंग बट डिस्प्रिन जो हम लोग यूज करते हैं. सो दिस इज एसिटाइल सैलिसाइलिक एसिड. So this reaction is acetylation. So acetylation gives you acetyl salicylic acid. Name is acetyl salicylic acid. This is also known as aspirin, which is nothing but an analgesic. Analgesic, that is painkiller. That is acylation of phenols. Now next problem. A reaction of phenol with neutral ferric chloride. A reaction of phenol with neutral ferric chloride. This reaction is also used as a test for phenol. So phenols on reaction with neutral ferric chloride gives you a various colors: red, blue, green, violet coloration. So reaction of phenol with neutral ferric chloride gives you red, blue, green, brown, etc. So this formation of different coloration is also used as a test for phenol. This different color is based on the coordination number of the complex that is being formed. So first look at this. Phenol reacts with Fe plus 3. So this gives you FeOPH3. This further reacts with phenol when this gives you FeOPH4 minus. Further reacts with phenol FeOPH52 minus. Further this reacts with phenol to give you OPH6 3 minus. So the formation of this various complex gives you various coloration. So this is used as a test for phenol, that is neutral ferric chloride test for phenols. And the next problem we have, again look at this phenol. Phenol reacts with bromine. In both the case reaction is with bromine, but there is difference in the medium. Phenol bromine dissolved in CCl4, this is non-polar solvent. Phenol reacts with bromine dissolved in polar protic solvent. So in both the case, now look at this reaction is bromination of phenol. So both reaction is bromination, that is electrophilic substitution reaction will take place at bromine. Now look at this. This OH group is a strong electron releasing group, so which increases electron density at ortho and para position because of resonance. So this is a strong activating group. So substitution, that is bromination, will take place at ortho and para position. Now bromine in presence of CCl4, this is generating a weak electrophile. So in presence of weak electrophile, the product form will be substitution at ortho and para. So a mixture of ortho and para bromophenols will be formed. Whereas when this phenol reacts with bromine in presence of water, this is generating a very strong electrophile. Very strong. What is happening is, look at this. Br2 reacts with H2O. When this gives you HBr plus HOBr. Now this HBr gives you, this is acid, so HBr gives you H plus and Br minus. So this H plus and further reacts with HOBr. When this gives you H2 positive Br. So because of this O positive, this bond is much strongly polarized, giving you a very strong electrophile. That is very strong electrophile. So we have a strong activating group, we have a very strong electrophile. So all ortho para positions will be brominated. So when this gives you OH, all ortho and para position will be brominated. That is 2,4,6 tribromophenol will be formed, which is white color precipitate. So this reaction is again used to differentiate from phenol from other substituted phenols. So pure phenol on reaction with bromine water, tribromophenol is formed, which is white color solid. So this is used as a test for phenol. If suppose chemically we have to differentiate this phenol from other substituted phenols, then we can carry out this reaction. Any substituted phenol will not give this tribromo, but this phenol on reaction with bromine in dissolved in water gives you tribromophenol, which is white color precipitate. So these are some of the reactions that we often comes when we study phenol. So more important reaction is the electrophilic substitution reactions. So these are some chemical properties, some properties based on the preparation of phenol. So hopefully you enjoy this problems on phenolic class.